Welcome back to Wheeled Mobile Robots. So you know this course actually took at least a small elevation. So we started talking about what is mobile robot, then we were talking about what is degree of freedom, then we address basic kinematic model for a land-based mobile robot, then we just come and address what is degree of maneuverability, and then we moved a little forward. So now this particular lecture we would be talking more about how to actually understand the system. We have derived the kinematic model, so how to actually make it more fruitful way. For example, you want something like the motion need to be simulated, or you want to make a closed loop, even the basic what you have seen a forward inverse kinematic model. So for that what one can actually see, we will try to do a simulation in the first case. So the computer based simulation what we are trying to see in this particular lecture. So that is what the lecture 5. The lecture 5 is all about kinematic simulation of a mobile robot, that too specifically what we call land based. So we are not giving anything in detail whether it is actually like wheeled mobile base or legged base or track base. We are taking a generalized equation which we derived in the lecture 3, and that equation we are actually using it and going further. And I hope this is the last lecture of this particular week. So I hope at the end of this week you can actually do your own simulation by looking this video, and you can actually get more understand, you can say you can get more clarity on this particular topic what we have talked about mobile robot kinematics. Let us actually move forward. So we will actually take what one can see this particular case. I'll just run through the mobile robot kinematics equations. I'll not be putting any time on that. But what I am actually interested to show here, we would be seeing the kinematic simulation of the land-based mobile robot with MATLAB, you can say equations and script. So that is what we are actually interested. So in that sense, I may actually switch over to the screen to a MATLAB, you can say window, and please actually cooperate. Sometime the font size may be smaller. So I have already tried my level, so we can see that in the upcoming video session. Okay. So now you know this is what we have derived. In fact, lecture 3 and lecture 4 I have emphasized this. So what we obtained this equation we are derived in this form. So now what we are trying to see, if I given this j and if I give the input command, can I find x dot, y dot and psi dot, and can I integrate that and get the x of t. So you know like this is time derivative, I can integrate it and get it. So in this case it may be look like straightforward, but what would happen if you are having a complexity? So what one can see, we will do the numerical integration, right? So in that sense, so we are going to do the numerical integration in this particular lecture. So that numerical integration can be done in several ways. So we are going to use one of the simplest method just for understanding, not for anything else. So just for understanding, we are going to use simple, you can say approximation method we call Euler method. Okay, that we will see little later. Right now what we are trying to understand, so we are trying to simulate the system based on the forward differential kinematics, and if time permits, I'll actually attempt the inverse kinematics for given you call position trajectory, can we find the input command velocity. That's what we are trying to see. So we'll actually go little forward. So in the sense what we are trying to do, this particular lecture is mainly focus on the kinematic simulation of a mobile robot. So what we would be taking? So we would be taking these equations. Okay. So where x dot, y dot and psi dot we are writing in a matrix and vector form, that is what we are going to integrate and do it. So simple sense what we can see, simulation here what we are trying to do, we are trying to do a ordinary differential equation solving. In the sense we are trying to write a code for ODE solver. Okay. So that is what we are trying to do. So I hope you got what we are trying to do. So I will be using the MATLAB script. Later on we can see if actually over you can see probably 1 or 2 weeks goes, then we can go with probably block diagram based approach what you call Simulink script. But right now this particular lecture would be focusing based on the MATLAB code. So for that I am actually switching the screen. Okay. So this is the MATLAB window which is actually coming to my screen, and I am actually trying to take everything on the script. So I am taking the new script. Okay. So I hope you are able to see the new script now. So now what I am trying to do, I am trying to do a kinematic model simulation. So I am actually writing that as my you can say section title. So I am writing actually like kinematic simulation of a land based mobile robot. So this is just for a title I am just giving, so that you will get an idea what I am writing on the MATLAB script. Later on you should not get a panic thing, what happened this. So in order to get this, so I hope you know what is Euler method. If not, I will actually like orally give a small idea. So that is what I can do in this particular lecture. Probably when it comes in the dynamic simulation, I may take a slide and then show you. Right now imagine you take a profile or the function. So function is actually like I can write as x, so that x is actually like depend on the time. So x is function of t. So now that is actually like draw in a time versus x profile. So now I am taking a small segment where ti and ti plus 1. So now this segment I am taking further on the curve, where it hitting on the curve, that is I am taking ti hitting, that is I am calling xi, where ti plus 1 what hitting I am taking as xi plus 1. So now you can see this is the segment which is actually like ti plus 1 minus ti, this is I am calling as a step size, which is delta t I am taking. So now corresponding to that equation, or you can say the curve where xi and xi plus 1 coming, you approximate this into a linear, in the sense I draw a linear straight line, in the sense linear curve between xi to xi plus 1. What would be the slope? The slope would be xi plus 1 minus of xi whole divided by delta t. So now what we would be assuming that the initial condition is known for solving differential equation, because it is an ordinary differential equation. One of the boundary condition which is we call initial condition, where xi is known, okay, and delta t is known, and this is what you call slope of that. So in the sense time derivative of that function also known. So in the sense what you can see, so x dot of I, xi and delta t, these all are known to us. So now what you can see, I can rewrite this equation. So how I can rewrite? So x dot equal to xi plus 1 minus xi whole divided by delta t. I can rewrite into what I can write? So xi dot multiply with delta t is equal to xi plus 1 minus xi. So which I can rewrite into xi plus delta t into x dot I equal to x I plus 1. So now what you can see, I can propagate from 0 to 1, 2, 3. So this is what we are trying to do. I think if I write the MATLAB code, you will get a clarity. So this is what we call Euler method. So now based on the step size what you are taking, delta t is actually like making the exact solution, or you can say awkward solution, I can say, not approximate, okay. So in that sense we will come back to the you can say case just for understanding. So I am just giving the workspace supposed to be clear, and the command window also I am clearing, and if anything as an image or figure, that also I am closing. This is just for basic information. Now what supposed to be known? This is actually like ordinary differential equation solver. So I am trying to do that with ODE solver. So for that I need to have a simulation parameter, right. So the simulation parameter what I call, so delta t, which I am writing as a dt, this is what I call step size. I am taking 100 millisecond, which I call step size, okay. So then I am taking a simulation time from 0 to what long the simulation is supposed to run. This I am calling TS, which is what I call simulation time. I am just taking as a 10 second, later on we see how to change. So this is what you call simulation time, in the sense total simulation time also you can take, okay. So now what would be the next one? We need to make this as actual expand. I am just taking as a t. T would be spanning from 0 to you can say Ts with the interval of say delta t, in the sense here dt. So this is I am calling time span, okay. So these are the simulation parameter, because we are taking a Euler you can say integration method. So only delta t and the simulation time is the important case. So we have come. So now what I am trying to do, so I am trying to give the you can say system parameter here for solving ordinary differential equation. What one can know, one should know, so the initial condition. So I am just giving the initial condition. So initial conditions what I am calling is eta of 0. So for that I need to know x position, y position and psi position. So I am writing x naught is my initial x position and y naught is actually like my initial y position. I am assuming everything as 0 and psi naught is actually like again the orientation, that is also I am assuming as 0. So now what one can see, so these are actually like initial conditions that need to be written as in a vector form. So that is I am writing eta 0, in the sense it is the initial condition. I am just writing as x0 and it is a vector. So I am putting a semicolon so that it would give us actually like vector, which is actually like column vector it will give, then psi 0, right. So now this is actually like my initial. So what I need to know, I need to actually like propagate, so x0 to xn plus 1, right. So obviously I need to refer as a x. So here x is nothing but a vector called eta. So I am just writing eta of 1. So this is a vector. So that is why I am actually like denoting. So there would be 3 cross 1. So this you call the colon will take forward whatever the number of, you can say, rows that would take, and there is a number of column is 1. So this is equal to eta naught. In the sense the first value of eta would be eta naught. Okay. Now we were actually like going to the for loop. I am writing loop starts here, sorry, just for understanding. So now what we did, we gave initial condition and simulation parameter. Now we are running. So there are several possibilities. I am using a for loop for simplicity. So for loop I am taking a, you can say, the loop constant or loop, you can say, variable as I, that start with 1 and it goes up to length of t. The sense I know the t is a span where it start from 0 to ts with the interval of delta t. For example, I take 10 as the ts and the step size is 0.1. So now how many? 101 as the total length. So 0 to, you can say, 10 with the interval of 0.1. So that is what, for 1 second it takes 10 sample. So it starts from 0. So then you can see that 10 into 10 plus 1 as 0. So 101 times this loop will, you can say, work. That is what the idea. So now what we need to know? We need to know what is actually like your Jacobian matrix. So the Jacobian matrix I am writing as J psi. So this J psi would be having what? Cos psi minus sin psi. So please excuse, I would be little slow in typing, but this is the way I can actually like make sure that you are following me. So cos psi. So this is the, you can say, Jacobian matrix we obtained. So this is what the Jacobian matrix. Now you should know like what is psi, right? The psi is actually like a variable. That variable is actually like what? The third row of eta, right? That is what your psi we represent. In the sense I am writing eta and the third row and ith instant. For example, if the loop start with 1, so the 3 comma 1 would be your psi 0, that is what psi, right. Now it goes the second loop, then the psi would be like eta of 3 comma 2, that is what we are writing. So now you can see that this is what the thing I am writing, this is current, you can say orient, this is the current orientation, but in radians, that also should be known. Okay. So this is what we got it, and this is the Jacobian matrix, right. So now you got some kind of idea, right. So the Jacobian matrix we have written. So what would be the final case? So you should know like what is eta, right. Eta is actually like integrating with respect to eta dot, but for eta dot what we know the relation? We know the relation is eta dot is j psi multiply with zeta. So now I am putting zeta as the vector, okay. So that would be actually like I call as UVR, right. So this is what we have obtained. So for that I need to mention what is U. So U is actually like I am taking 1, so which is I will write long, I think I will write as U is actually like x axis velocity, that is EC, because longitudinal lateral will not be represented when you go in a proper plane, because that would be associated with the body x axis velocity with respect to B frame. That is what, this is the instantaneous velocity, right, at instant. So, this is what the velocity. Right now I am putting this as 0, this is y axis velocity. B frame, right. So, then what you should know, R. So, R is actually like your angular velocity. So, since it is a land base, I am not writing which axis, but this is actually like with respect to z axis. This is z axis angular velocity, that with respect to B frame, right. So, now in the sense you can see that these are the things we obtained. So, now I will bring that equation. So, now what we know, the eta dot, I will write eta underscore dot means it is eta dot. So, that is actually like at ith instant. So, I am writing that is a vector, the ith instant would be equal to, so zeta, this also I will write as ith instant. So, now what would be that, the j of psi, okay, multiply with zeta of ith instant, right. So, this is what we know. So, further what we can actually like see, the eta of, you can say I plus 1, we can actually like get it what way. So, eta of I plus dt into eta dot of I, right. So, this is what Euler method, okay. So, where the you call dt is the step size, and you can see, right, whatever we have written that has come. So, now everything has done, right. So, that is also you have actually like make it. So, I am just putting end. So, the loop ends here, and then if you run it, what one can actually like find. So, for given UVR, so you can find eta time profile. What that means? So, it is actually like the forward differential kinematics you have already solved, but you want to know like how this goes further, right. In the sense you want to know like what would be the U profile, what would be the x dot profile with respect to time. So, these all need to be known. So, for that what we need to know, like I will just put it. So, plotting. So, plotting functions start here. So, I am just plotting first. So, plot of, so t. So, t is actually like already defined as a span. So, that would be actually like I am planning to show. So, the eta 1, which is nothing but x, that would be actually like going further. So, why I put 1 is to I, because the eta would be actually like I plus 1 instance would be there, but you know time is actually like up to I instant. So, I am actually like putting eta as up to ith level, so that you can plot that. So, I am just showing this is red color, okay. So, and I am just putting, just you call get, I will just put the set, the figure, whatever, the font size I will just make it so that you can actually like able to see, probably 24 I will put, okay. So, x label would be here is actually like a time which is in second, and y label would be, you can see x, which would be in meter, okay. So, this is just for showing. So, we can see. So, for understanding I am just giving a slow speed, because the mobile robot will not go you can say not more than 0.5 meters per second. So, in the sense I am just taking a very slow speed. Earlier I gave 1 meter per second, now I am taking it is 0.1, because then only the plotting would be actually like reasonable. So, now if I run, I hope there would not be any error. So, I will just run. So, obviously MATLAB will ask you to save. So, I am just saving it as you can say kinematic model, of mobile robot. And one thing I can actually like give, so while you are saving MATLAB code, you don't save with the starting with the numeral, okay. So anything which is actually like a numbers, the numbers will not be addressed in MATLAB. You start with some, you can say alphanumeric, okay. So now I saved in a general form, you can see that already it was running. So you can see these are the animations, so that's not required. So you can see that I ran the simulation for 10 seconds. I gave, you can say, longitudinal velocity of 0.1 meter per second. It actually like move forward, right? You can see 10 into 0.1, how much it would be? 1 meter. So that's what it is actually traveled 1 meter, right? But this is actually like not really the interesting thing. Why? Because this is not giving any intuition to me, right? The intuition will come by, you can say, animate the system. For animation, so you need some additional tool. I hope actually like the animation can be done in the next upcoming lecture. I'll show you. Right now I will show you like the other parameter how you can actually like see. So for example, I am giving this is 0.05 and you can see the initial point is actually like 45 degree, which is actually like pi by 4. So you can see earlier it starts with 0. So I am just trying to plot, okay, I am just plotting 3 different plots. So I am just putting as this is a figure. So I assume that you know already MATLAB, that's what I am not at all actually like touching anything behind the MATLAB picture, in the sense MATLAB aspect. But if you have actually like issues, so you can actually like go through several, you can say lecture videos are available on MATLAB, and that too like for engineering cases. So we will actually like see a little more detail in the MATLAB code here itself. So right now I am actually like taking it, this is a blue color and this is actually like green color and this is actually like not, this is actually like psi, okay, and this would be what you call, this is in radians, okay, and this would be y, and this is the case, right. So if I actually like run, this would be plotting 3 things. So one would be time versus x, time versus y, and the third thing is time versus psi. So we can see whether it is first of all running. So later on I will show you, because we have taken the psi is actually like pi by 4, which is nothing but 0.707 approx, not 707, somewhere it is a 0.89 or something. I just check the value. So I forget what the exact value. So but you can see this is equivalent to pi by 4, and that is what it is actually like showing, and this is actually like y is actually like moving with the velocity of 0.05, or how much I give, I just check, it's a 0.05, and x is actually like moving with 0.1, right. So these are the cases and you can actually like see how it goes. So these are the aspect one can actually like see it, okay. So now you can see that these UVR, which are actually like coming directly you are giving, but this is supposed to be written in the case of what you call based on the angular velocity of the wheels, right. That's why we address the equation, one equation we have written, right, the zeta we can write in terms of w into omega. So that you need to actually like do it. So next class we will actually like address that into very detail, and similarly I will be showing the animation. So how to actually like make one of the block, that block is actually like moving on the given plane, because it's a planar robot, right. It is very easy to simulate and animate. So the next class I will show you one additional you can say aspect of this kinematic simulation, and then actually like we can move forward by introducing the angular velocity relationship of the wheel, in the sense you will bring the wheel configuration and then try to simulate. So the next class, so probably we will do the kinematic simulation in the beginning, then we will actually like move forward to the, you call the wheel model, and then we will actually like incorporate the kinematic model along with angular velocity of the wheels. So with that I am actually like closing this particular what you call the small simulation session. So then the next video would come with animated video along with inverse kinematic solution, okay. So right now we have given simple forward kinematic, because I don't know like you are comfortable or not. So you take a while, because I just introduced the MATLAB, And you can see that we have not done anything. We have started simple Euler integration for the solving of ordinary differential equation, and we have taken the initial condition, and we have taken the straightforward forward differential kinematic relation, and we have substituted and we took the numerical integration and plot the function. Now this is not enough for understanding. We will do the animation in the next lecture. Okay. With that, I am saying thank you and see you then. Bye.